examples of this. If you look at standard maps of America, of Europe and all the rest, what does it look like? You guys remember?
We're the largest countries.
Yeah, but they chose a selective map projection to do that. If you actually look at from space, what we really look like in terms of area, we're way smaller than a lot of the other countries, but they don't tell you that. It's a selective use of a map to make us look like we're at the center of things. And there's people in geography and elsewhere that's saying there's a political and maybe ideological, maybe even racist element to that as to why that's been emphasized over time. Interesting stuff. Anyway, so there's that. Then the other one says, now instead of two lines that never meet, that go parallel, so we have two lines that never meet, they go parallel. We also got two lines, but they converge, they do meet. Now the opposite, two lines that not only go parallel, but they get further and further apart. What does that look like? The closest you can get to that is, think of this as like the horse of a saddle horse, or the saddle on a horse, right? It's 9 degrees there, but the idea is, as you go further out, things diverge, they start falling apart. These are called hyperbolic geometries. They go in the opposite way, okay? All right, so you think, that's all great, they studied this, big deal. This is all just logic and math and just blowing smoke, it's all theory, who cares, right? No application. Einstein comes along. Einstein's famous one.
Theory of relativity.
Yes, E equals mc squared, all that kind of stuff. Does anyone know? Yeah. E equals mc squared, interesting, but who cares? Einstein comes along, he's famous for theory of relativity. He's thinking about the structure of what's called space-time, and it turns out that, lo and behold, the very thing that he's thinking about, he needs a way to express this. Because if you look at any physics book, what is it full of?
Physics.
Yeah, sure. And what is the language of physics?
Math.
Math! There you go. What underlies physics then?
Math?
Math.
Mathematics.
If you look at a math book, it's full of all these funky symbols and whatnot. What do you think holds math together?
Logic.
This is not totally true, but close enough. Logic actually is the glue holding math together. It's the foundation. We good? Okay, so he's coming around, he's studying physics, he needs a language to describe these ideas. Math is the language of physics. It's often said that mathematics is the key to the universe. Turns out these non-Euclidean geometries are exactly the sort of thing that fit the structure of the universe. This goes back to that ancient notion of logos, the Greek notion, word, reason, logic, in this case pattern. And why it is that what goes on in our mind maps onto the nature of the universe is one of the deep mysteries. Why should it be that when we think of this stuff, which seems totally made up, totally without any application whatsoever, it actually applies exactly to the structure of the universe? Yeah, that's logos embodied. Here it is, logic at the basis of how our universe works.
Well, that makes sense. That would be how Isaac Newton invented calculus to prove his theories.
Yeah, but I mean, why should that kind of stuff even map to the universe at all? I mean, if you looked at logic and what we're doing now, would you think it has any application? No, in computers and whatnot, but yet it does, over and over again. So that's, again, one of the deep mysteries. Anyway, think of it like this. He talks about this notion of space-time. You can think of it like a sheet. Space is how many dimensions? 3, right? Like that. Left, right, up, down, like that, right? What does it make sense to talk about a 4-dimension? Can you even imagine it? 1 dimension is just a line like that. 2-dimension is, it's a 9 degrees, so it's separate. It creates a space, like you guys remember Cartesian coordinates. 3-dimension says you find a 9-degree angle between both of those. So we can imagine that as extending your space out. But then a 4th dimension, you can't even imagine it, right? Yet Einstein says this is actually the world we live in. It's a 4-dimensional type of universe, 3-dimensional space, and 1 of time. Okay? The image he gives to understand this is, think of a rubber sheet. Drop a bowling ball in it. What happens to it?
It's going to bounce off.
It curves down, right? If you throw another, say, marble at it, what is it going to look like when you throw the marble on that sheet? It goes round and round and round. That's the image of how gravity works. Why does gravity work where you got planets rotating around the way they do, supernovas forming the way they form? It's because time, space and time are curved in this way. His general theory of relativity takes these non-Euclidean geometries, talks about how space and time are warped in these ways using this logic stuff. This stuff is really real. To give you an example, I think I talked about this before, but I'm not sure. Did we talk about the twin paradox?
Oh,
No?
like having the same person?
Yeah, the twins, and they leave.
Yes.
Oh, one
They
stays.
talk about that. One gets adopted, or they're raised in different areas, but they do the same things, like
Kind of.
carpenters afterwards.
No, I wouldn't talk
Or
about
one
that.
stays on the ground and the other goes
On a
space.
spaceship.
Yeah.
Did we talk about that?
No,
Say it again, please.
I don't think so.
Twin paradox. It's an implication of this stuff. So they've actually tested this. It's real. It's not like science fiction. It's really real. Okay. So the twin paradox goes as follows. You got these two twins, same age, right? One of them stays on Earth. Another one goes on a spaceship, travels to the end of the galaxy and back. That's the science fiction part, not really real, right? He's going really fast. What do you think happens when he comes back, say after 30 years' time?
Ages. He's
Who
the same
ages?
age, but his twin is aged older.
There you go. The guy on Earth is 30 years older. The guy who left, who traveled at near light speed, comes back. It's like he hasn't aged a day. And you think, well, that's cute and interesting. They did the following experiment. They took atomic clocks, which are about as closely calibrated as we got, right? They had one on the ground, and they put one in a plane, and they had it fly around the Earth a couple of times, okay? The idea is, it's called relativistic physics here. Relative to these two time frames, the faster you go relative to the other thing, the slower time goes. So that you might think, look, you're going in a plane, you're going pretty fast, but we're talking about speed, like going at near the speed of light, which is way faster, right? So there's more local scale. They said, take these two clocks, calibrate them so they're going exactly the same. They start, it's like a stopwatch, right? Ding, they start at the same time. They flew it around the Earth a couple times. When they brought it back, they found that it correlates exactly to Einstein's equations. They were off by just a slight amount. This is what's called time dilation. So time, space, they're not what we think of it. We think of time in this local way. We live, we're born, we die. It goes in this linear fashion. But real time in the universe, it's far stranger. Kind of makes sense?
Totally.
Okay. So that's one application of this stuff. Here's another. It connects up historically. So here's the part with M.C. Escher. M.C. Escher, who's he?
German artist.
There you go, a drawer. He did all these things. Interesting photos. Interesting pictures, artist. You can Google it if you want. Google M.C. Escher. He's not like Master of Ceremonies. It's not like M.C. Hammer, Microphone Escher. No rapper or anything like that. It's just this, his real name is hard to pronounce, so they said MC, right? So, click on images. These are all these interesting things. He was very mathematical. He didn't realize it. He wasn't trained as a mathematician, but mathematicians love this stuff because it's almost like mathematics if you were to visualize it in art, yeah? So you got what are called, for instance, tessellations. That's the fancy word for it. Take a look. You guys have seen this before, probably.
Mm-hmm.
It's the fish. And then you follow it up, and what happens?
Turns into a
It's a
bird.
bird, right? You take the negative space, it co-defines the positive space, and it turns into something else. But it's the same thing, just variations on the same thing. All right, there's that. That's cute. Who cares? There's the hand drawing itself. That's recursion. How can the hand draw itself if it's drawing itself? If it's in the process of drawing, what? That makes no sense. Oh, maybe it does.
Oh, actually, M.C. Escher was an inspiration for a statue in the country of Georgia. If
Really?
you scroll down, you'll see it. It's on the, wait, go up a little bit more. Stop, up one more. On the left hand, so your right hand
This?
side, that one. There are two statues that are shaped with the spiral in between, and they go through each other.
Ah, that's actually more interesting. I didn't realize it. Why Georgia? Is there a connection?
Oh, there's like some romantic cultural thing that,
Oh, okay. They did it way back when. It
Yeah.
just sort of slipped
and then they use that M.C. Escher principle to tell the story.
to draw. Okay. That's great. It's good to see that. There's a bunch of these. Here's an apparently impossible drawing. So you guys take a look at it. Some of you seen it. Great. Don't say anything. What's wrong with that? It's a waterfall. How cute. What's wrong with it?
Water doesn't go up.
Why not?
How come the water wheel isn't spinning?
So follow the water. Water comes down, right?
Yeah.
If it's going down,
But it's
Oh.
going.
how is it happening?
Oh, cool.
Cool.
It's
But
defying
how's it
gravity.
happening? It's not happening.
Yes.
No, it is happening. Cool. I don't know. Everyone's got different reactions.
Oh my god, it's just like the movie Labyrinth. Okay.
Okay.
Trippy.
Here's how he did these. He was actually interested in these non-Euclidean geometries, the way in which space bends back on itself. Like I was saying, Einstein was thinking about these things about space bending back on itself. We think of like time warps. Those are really real. These are consequences of Einstein's relativity. Time travel is in principle possible. Whether we'll actually do that is a totally different thing. When they talk about wormholes and like sci-fi, it's taking space and bending it back on yourself. That's a consequence of what he's talking about. With these non-Euclidean geometries, you can think of them as just all these weird ways in which space contorts and contracts and does strange things. He studied this stuff and he was thinking, how do I actually incorporate that into my drawing? So he asked a bunch of mathematicians studying this stuff, and he found ways in which to impose these principles into his drawings to create these seemingly impossible things. Yeah? So latent within a lot of his drawings are the very things I'm talking about there with non-Euclidean geometry. So if you want visual examples of what we're talking about with non-Euclidean geometry, framed by this axiomatic method, there it is. We good? Okay, that's it for the entertaining lecture. Let's go back to the boring stuff. So back to null quantification sentences. I'm going to use one of those ideas there to talk about here. Null quantification, it says open that up and then open up Gödel's world. Gödel is this German, Austrian logician and mathematician. He is considered to be maybe the greatest logician of all times. The only reason we do this exercise is I feel some responsibility to talk about Gödel. It's spelled G-O-D-E-L, but there's an umlaut on the O. It's like Gödel. I can't do it. He was friends with Einstein. How often? You think everyone says Einstein's smart? He's like a genius, right? And he was. Gödel was a friend of Einstein. He makes Einstein what he did look like child's play. I mean, we're talking about magnitudes of smartness that's just above, and you don't hear about it too often. How smart is the guy? They were talking to each other. They're buddies in Princeton, right? And Einstein said, "I'm working on this stuff, general relativity. I haven't quite put it together." And he says, "Oh, tell me about it." And he tells him about it, and they start riffing and jiving. Like overnight, actually a couple days. Gödel, just for fun, basically takes those ideas and goes into mathematics and comes up with Einstein's theory of relativity in different format, just for fun on paper, and then he puts it on the side. Einstein later comes up with the actual full-blown correct theory, gets all the credit for it, but Gödel did it in the span of just a couple days for fun's sake. That's how off the chart smart this guy is, okay? He basically laid foundations for any number of things. But here's one thing which he's probably most famous for. It's called Gödel's theorems, incompleteness theorems. And they go roughly as follows. I'm not going to do an exact rendition here, but it's close enough. I'm going to try to make it a bit entertaining. Okay, so let's frame it in terms of what I had on the board before with the hierarchy, right? So you think science. I mean, science gives us our most sure knowledge insofar as we have knowledge of anything, right? Imagine, suppose we don't blow ourselves off the earth, there's no environmental catastrophe. We actually make it, let's say, millions of years down the line, right? Without screwing ourselves over. Nuclear weapons or some bioweapon, who knows what, right? Because there's any number of ways in which we can collapse. We make it that far, you think we're going to be the same species?
No.
I mean, think about it. 100 years ago, totally different environment, right? No computers, barely even flying machines. Everything's transfigured, right? So imagine not just hundreds of years, but millions of years down the line. When we look, assuming you get progress, and progress goes in leaps and spurts, assuming you keep going up that curve, we're not going to be anything like the same creatures we are now, right? In fact, at some point, we'll probably start messing with ourselves, transfiguring ourselves. This is what they mean by sometimes what they call it singularity I talked about before. There's a kind of transcendence of our natures. We become something else entirely. Maybe our consciousness gets lifted out of our bodies, put into a different kind of platform. We think of computers now, but imagine something way more efficient. We're actually in the ether, in the air, our consciousness distributed. We're just totally unlike anything we can imagine. Kind of good? Okay. If they came back to us, millions of years, human beings evolved to that point, what would they look like to us nowadays?
Aliens.
Aliens, maybe even godlike, right? Or something divine. So we think, okay, science and technology are the road to get there. So here's the question. Is there in principle anything that science cannot discover? You might say, well, give me a candidate. Who says, yes, science can't discover everything? Be honest, you're pretty theoretical. Okay, so some of you are like, yeah, it can't discover everything. Who says no? Okay, so there's varieties
Science
here.
can discover anything?
In principle, is there anything it cannot uncover or understand or expand upon?
I agree.
You say yes?
I say yes.
And who says no?
You know what?
It can't, there are limits to what science can do. Yeah, good. So, like, what are some candidates for things science cannot do? Will it ever capture the nature of what it means to love?
Oh, yeah.
Or, not yet, but maybe some people say maybe in time, right? Others say, no, it'll never capture the nature of what faith is about, which is a leap beyond what we know. Faith is always there.
Can it read people's minds?
It can't read people's minds in all its details. It can give you rough sort of
I feel like all
general-
these things, science can eventually
They will.
answer.
There you go. So that's the big question. Can it or not, right? And this is an open philosophical debate. You might say, we don't know. Maybe it can, maybe it can't, right? So that's why I said, imagine millions of years down the line. Maybe at that point we can answer these questions, but still, maybe not. There might be unexplored mysteries that we don't know of, right? Even at that point.
I think the more science we do too, the more we won't know, actually.
There's that version too. Amongst even prominent scientists, Nobel winners, they say the more you actually get into science, the more you know, the more you realize the unbelievable amount we have no clue about. Yeah. So it varies tremendously. Here comes Gödel. Okay, so let me try to frame it in terms of what I had on the board before. Science is composed of mainly those various fields, right? Biology, chemistry, natural science, and so forth, right? What underlies the fundamental of all the sciences? Physics? Math, right? And what underlies that?
Logic.
More or less logic. That's not exactly true, but more or less. So math and logic, it's in a sense our gateway to the various scientific theories. You open up any textbook out there, physics especially, it's just rife with mathematics. So if we're talking about science can in principle unlock all the secrets of the universe, it's going to have to be tied to math at some level. We kind of good? You guys with me? Okay. So the equivalent question is, how far can science go? Is basically the equivalent question to, how far can math go? Does it have any limits? We kind of good so far? Gödel actually came around, and this is where he proved what's called his incompleteness theorem. He's basically said, for any system of mathematics powerful enough to do basic arithmetic and beyond, and that's all the stuff I was talking about, the non-Euclidean geometries, calculus, higher level math topology, all this stuff that's really exotic that you guys have probably never heard of. That's basically all of the field of mathematics. He actually proved, like we did in the Fitch proof, but way more complex, he proved that for any system powerful enough to do this basic mathematics, there will always be things in the system that you cannot prove. There were things that in the system you cannot prove, and he proved that. What does that mean? So that's weird. So one way, a popular way in which it's been interpreted is as follows. No matter how far science gets, no matter how far our body of knowledge gets, there will always be things within our system of knowing that from that system we can never, ever actually prove. And you can prove that. The way in which this has been interpreted is that there are at least two realms built into the structure of not just our knowing and our consciousness, but perhaps into the nature of the universe itself. One is this expanding body of our knowledge of what we can know. And then there's this stuff out there, call it the fuzziness, of things that we can recognize as true, but we can never actually prove. And he proved this in the mathematical theorem now. So the interpretation is, even if, no matter how advanced we get, millions of years from now, we're totally different species, we know pretty much anything. If they came back to us, we think of them as like godlike, maybe even God, right? And you see these sci-fi movies, advanced species come back, we think of them as deities, right? We don't know. But the point is, no matter how far we get, there will still be things outside of that realm that we can somehow recognize as being true, can never actually prove, ever, okay? One candidate for this, some people have speculated, is the nature of consciousness itself. Consciousness turns out to be, the more scientists study this, we think galaxies are hard to understand. Turns out this thing in here, not just the brain, but consciousness, may be the most difficult thing to understand in the whole damn universe. This is considered to be the cutting edge of science. We try to understand this, the more we try to understand, the less we actually understand about it. Neuroscientists and others, they basically say, yeah, we'll get it eventually. But other neuroscientists who study this stuff also, they're saying, we have no damn clue. This is how it works, right? So one claim is, consciousness itself is one of these things. We can recognize certain claims as being true. Maybe metaphysical truths, but we can never actually prove it. So they might claim like things like, when you make a leap of faith. We know that consciousness exists, but we can never actually show what that is. Or we know that maybe God exists, maybe, right? But we can't actually prove that. These are what are called big metaphysical mysteries. And the claim is, from the stronger interpretation, that these things will forever remain mysteries. Even if we can recognize them as true, we can't prove it. So there's limits to what knowledge is about.
So he proved that theory?
He proved, not quite that, that's the interpretation.
Oh.
He proved that mathematical systems, if they're basically powerful enough to do higher level math, there are always within those systems things that are recognized as true, which can never be proved. And he proved that you can never prove it.
There's limitations in?
And so the interpretation is there's limitations to what we can know. It's not like give science enough time and faith enough time, we'll get it all. The claim is there will always be mysteries. It's built into the structure of, yeah, it's crazy. All right, back to the plain note homework, here we go. So null quantification, what you're doing here, null means what?
Nothing.
Nothing, like if you write a check and it comes back null and void.
There's nothing at
No money in the bank, null is nothing, right? So if you look right here, EV, that's the parent. Does it bind to any kids?
No.
No, remember the image I used before, deadbeat dad? No kids, right? So get rid of it. So what is this equivalent to?
is back in the snack.
Yeah, just back of BC. So that's all we're doing here. Null quantifiers, get rid of them. There's a null quantifier right there. Count it out. 3. What's wrong with that?
No.
There's no-
Kid.
No
There's no
parent.
X.
It's all right.
Dodic B.
Okay, so Dodic B. 5. What's the null quantifier there? EX is not doing any work, right? So drop it. What do you got here?
Oh.
Cube C and small c.
And Small c, there it is. 8. Okay, you got two quantifiers. Which one's doing work?
The A,
AY, right? So which one's not doing any work?
the EX.
So you just drop it. There it is. 10 is the only one that's a little tricky. Okay, so take a look here. You got, what are your kids?
Y.
Y. What are your parents?
A,
AY and EY. Who got there first? You got, this is parent, like parent custody battle over the kids, right? Divorce settlement. It's no good. So you can't have that in logic. Who got there first?
the A.
The AY was there first, this is second, so it turns out the EY you can drop. And that's it. That's all we're doing for this assignment. Like I said, today is more theoretical. It's just more about talking about these variables. Let me shrink it and you guys can take a picture. Oh no. Alright, fine. We'll do it in 2 parts. There's your first picture.
So if you have a contradicting AY, EY, or EY, AY, if it's flipped around, the A, see if you had
The A, yeah, whatever is there.
whatever's in the far end, the far left is
Right, because that's like second on the scene, right? Yeah. Good? Everyone got it? Okay, that one. Last one. Second page.
Thank you.
Okay, some good news. 10.24. This I wasn't smirking for that reason. 10.24 is being dropped. Am I smirking or smiling? What's the difference?
You don't know the difference?
Is Mona Lisa smirking or smiling?
Which one is 2.26?
Isn't that the eternal mystery?
Did we just do?
So 24, 10.24 gone. So all we got is 10.26. So how many problems for tonight? 3, that's it. You guys ready? Can I close this? Everyone got it? Going once, twice? No. Just turn it in. And if you got to change something, change it. Oh, bless you. Bless you, soul loser. That's ridiculous, but it's so good. Okay, oh, no, there's no way out. No. Okay, Fitch.
Yay.
Yay, that's not why I'm smirking. I'm not smirking, that's why I'm not smirking. Because I'm not smirking.
So that was 10.23, right?
You what?
Dark. Okay, I'm going to enter this in, so let's put in what I got at 10.26. You notice I added a line after, there's nothing in 1. That's intentional. AX, somebody read it off to me.
AX,
Tet B,
Tet B,
if and only
if and only if E, W, Tet B.
W, Tet B. Okay, let's think this through. So applying the null quantification thing, does AX apply to anything here? Does the AX apply to any kid? No, so effectively, what does this first half say right here?
All B,
All the
things
things
that
you have.
Does it? Does the X go with the X here?
No.
No, so does this do any work?
No.
No, so effectively what does it say? It's null.
Tet B.
Yeah, just Tet B, there you go. Not all B's are Tets, which is going to get you messed up because that makes no sense, right? Just Tet B, because the AX is null. And likewise on the right, the EW, does it bind to anything?
No.
No, so effectively that says
Tet B.
Tet B. So this says Tet B if and only if Tet B. Is that always true? Yes, because it's saying I'm the same as myself, right?
Yes.
The rule for that is FO_con. If you remember, FO_con is,
First order.
yeah, that's basically connectives plus quantifiers, predicates don't matter. That's the whole thing we did with the, was it Snuggly Wuggly, was a bear? I don't know.
Fuzzy Wuzzy was a
Nuggy,
bear.
yeah, no gold, no gold last time. No, not
Fuzzy Wuzzy had no hair.
Set that up. You have to set that up.
That's it. You save this approved 10.26 and we're done.
Word.
We'll have fun over the weekend with
Other
MC
homework.
Escher.
Did you open that from a file or did you do
No, I
it
just
from
created
scratch?
it. So you just
It's
one,
just scratch,
you add
yeah.
2, you stick it in, FO_con, you get the check, and that's it.
Approved.
26. Have a good weekend. We'll start it up again next time. Oh yeah, I forgot to mention, if anyone's interested in this stuff, interconnecting logic, Gödel, and all of this, what's called metaphysical stuff I was talking about, there's a book that's won not a Pulitzer? It might be a Pulitzer. No, it's not. It's something like that. It's one of the top awards you can get for writing. I don't know if I'm spelling this right either. Douglas Hofstadter. He's got a book called Gödel, Escher, Ross. You can check it out in the library. It's one of those, it's like Lewis Carroll. It's one of those things where you can read at one level, pretty entertaining, but it's a little bit difficult. You can read it after you take logic, you can get some of it. You can read it if you're even a seasoned logician. Got layers of meaning. Gödel's the guy we just talked about, logician. Who's Escher?
MC Escher.
MC Escher, the drawer, right? The artist. Who's Bach?
Johann Sebastian.
There you go. What does he do?
Classical music.
Classical music. You guys heard of a few? Okay, his music is actually the precursor to rock and roll. That stuff, rock and roll.
Oh yeah.
What's one of those guys who plays like he's like one of the best guitarists in the world? Mandelstein or something like that?
Mendelssohn?
No. Mango. He's like an electronic rock and roll guitarist. Forget it.
Which
Bach is the musician. You think these three things have nothing in common with each other, but what Hofstadter does is realize that in Escher's drawings and Bach's music, you see logical principles being unfolded in all of these, and they all connect up to Gödel. And then beyond that, his real quest in talking about these three things is just to talk about these nice parallels. The nature of what consciousness is itself and its mystery. It is something that we utterly take for granted, and it is utterly baffling if you think about it. We're done.
That sounds very interesting.
Have fun.
Thanks for giving away the plot spoiler for Interstellar.
Oh, sorry. Yes, that is it.
So if you're ever confused about black holes in space-time continuum, watch Interstellar.